Good morning, Physics 30. I hope you guys are having a rockin' Monday, or whatever day it is for you guys when you're watching this video, but it's always Monday, so hope you're having a rockin' Monday. And today we're going to be doing part 2 of our reflection and refraction notes, and today we're going to be looking at critical angle scenarios. So it's absolutely critical that you pay attention. All right, so ladies and gentlemen, bad puns aside, things not working. Maybe I should plug in the writing tablet thingy instead. That might make a little bit of a difference. I plugged it in. Okay, it's plugged in. There we go. Now we're working. Okay, so ladies and gentlemen, if we had a diploma exam, I would put a star here and write on test, because back in January, there was a critical angle question on the last diploma, but we don't have a diploma exam. Tear. Okay, so what the critical angle is, ladies and gentlemen, it is our incident angle. So remembering that incident means incoming of a ray or a wave that is going to be refracted to 90 degrees from the normal. So in other words, it's going to just run along the surface of the boundary. So if here is going to be our water and our air, that means that this theta here in comparison to the normal would be the critical angle. And then as it refracts, it's just going to scoot along the surface of that medium. Okay, so ladies and gentlemen, it means that our critical angle is our incident angle. Refracted angle is always going to be equal to 90 with that critical angle. So that is super important there. So keep that in mind. The refracted wave is going to have an angle of 90 degrees. Okay, always. And as well, in order for us to get a critical angle scenario, the wave must be traveling from a high index of refraction to a low index of refraction. So from water to air, say, or from a diamond. They're really small in my engagement ring. 76 years old. They were my husband's grandmother's, the wedding rings. Okay, so these, or so a light coming from a diamond out into the air, say, you could get a critical angle scenario. So, ladies and gentlemen, we will do a problem with that, for example, number 1. And then we're also going to be applying this to total internal reflection as well. Now, these are super cool because this is used with fiber optic cables. Okay, so, and as we all know, fiber optic cables are super useful for getting things like television and other types of telecommunications. Okay, so ladies and gentlemen, total internal reflection occurs when light gets refracted so much it becomes trapped within the medium. So as you see here, the light comes here, and instead of escaping to bend, it's going to bounce right back into the water here. And this bit here, ladies and gentlemen, these next 2 points are going to be important. So it occurs when the index of the medium increases from that of the critical angle situation. We'll talk more about this with example number 2. Okay. And once again, in order for this to happen, we have to go from a high index of refraction to a low index of refraction. And this is also going to occur when we have an angle greater than that critical angle. Okay, so understanding this is super important for fiber optics, and which we use in all sorts of telecommunications. Okay, so let's look at critical angles, some calculation scenarios. All right, so question number 1. Calculate the critical angle for the diamond air boundary if the diamond has an index of refraction of 2.42. All right, so let's draw our scenario here. So I'm going to draw my normal. That's my normal line. And that is going to be my surface boundary. Okay, I'm going to switch colors here so it's easier to see. And we are then going to have our light that's going to be coming in. Now remember, we have to go from a high to a low index. So this guy is going to be the diamond. And we know that we are going to have an N of 2.42. So our wave is going to come in, and then it's going to hit the surface of the diamond in the air boundary, and then it's going to scoot along the surface of that diamond. Now, also know, ladies and gentlemen, that our N2, will make this guy N1 because we can, is that of air. And what is that of air? Oh no, correct. Okay. And as well, because you have been told critical angle, we've been asked to find the angle that is coming in here. We've been asked to find this theta. However, we do have this theta here because of the term critical angle. Our refracted beam is going to come in out at a theta of 90 degrees. So that's the key thing to remember with that critical angle term. It means our theta 2 is going to be 90 degrees. So watch out for that. So, ladies and gentlemen, also remember, you have to have this from high to low N. Okay, so be very, very aware of that guy. Okay, that's the other term with thing to keep in mind with the term critical angle. So we're going to look at our data sheet, and well, I have theta. So looking at my data sheet, I have my sine theta 1 over my sine theta 2, which is what let's try this again. I have sine theta 2 and I want to find sine theta 1. And I have N1 and N2. So those are the values that I am going to use. I'm going to rearrange this so that way I get theta 1 by itself. I'm going to multiply by sine theta 2 on both sides. So I'm going to get my sine theta 2 times N2 divided by my N1. And in order to get my theta, I'm going to take the sine negative 1 in order of my sine theta 2 N2, that's supposed to be a theta, there we go, divided by N1. All right, so I'm going to plonk my numbers into my lovely calculator, and we are going to have my sine negative 1 of my sine of 90 and multiply that by 1. Okay, that's my value of N2. And then we're going to divide that by my 2.42, which is N2, which is going to give me the lovely value of 24.4079 degrees, assuming you're not having a rad time when you put your calculator in degrees. And with sig digs, our lovely 3 sig digs, we're going to have our 24.4 degrees. All right, so with critical angle scenarios, those are the couple things to watch out for, is that you have to set it up from a high to low end scenario, and that your theta 2 is going to be 90. So those are the things you were going to have to memorize if we had exams or if we had a diploma. So if you see them again, you need to know those. All right, let's look at number 2. So, ladies and gentlemen, as I mentioned earlier in the notes, our question number 2 is dealing with our total internal reflection concept here. Now, let's look at the question and determine how do we know this. So, when we read our question here, our minimum index of refraction the prism needs in order for the light, in order to follow the path as indicated in the diagram. Okay, well, we have a beam of light coming here, bouncing off the wall of the prism here, bouncing off here to then exit out. Well, ladies and gentlemen, we need to consider what our rays of light are doing here. So notice it's entering and then bouncing off that surface. What we have here is a case of total internal reflection. Okay, because that light, we can see that light getting trapped within this prism. Okay, so let's think about what we know about our total internal reflection scenarios. So what we looked at in the notes, what was mentioned earlier, is that your theta, okay, your incoming theta has to be greater than your critical angle. Okay, so you can go that way to get total internal reflection. Or our other method is that the N1 of the medium has to be higher than that of a critical angle scenario. Okay, so I'll write that down too. Okay, so remember with our previous question, unfortunately, technical difficulties, the computer deleted everything we wrote down for the previous question. But go back and look at your previous question. Notice how we were able to calculate our critical angle of that diamond. And remember how a diamond's N value was 2.42. So if we wanted to get in a total internal reflection out of that diamond, we could hypothetically increase that N value with that same angle, and we would then get total internal reflection. So that's what we are going to be looking at here. We're going to calculate the N value with total internal, we're going to calculate the N value at a critical angle scenario and recognize that that N of this prism must be higher than what we calculate for total internal reflection. So we're going to calculate N at a critical angle. Okay, so how are we going to do that? Well, first, we need to determine what our normal line is. Now, remember, normal is always perpendicular to the surface. So here is our normal. It is perpendicular to the surface where that ray is going to be bouncing off that surface, giving us our total internal reflection. Now, you have also been given theta here as 45 degrees. Well, ladies and gentlemen, this is at a right angle, so that's also going to be at a right angle there. Remember that the sum of all angles in a triangle is 180. So, well, 90 plus 45, and you take the sum of that, 180 minus your 90 plus 45, that's going to give you 45. So that means this theta is also going to be 45. So this is 45, this is 45. Well, ladies and gentlemen, guess what? We have a perpendicular to the surface line. That means this is a right angle. Well, 45 is half of 90. So that means that to the normal, which is the theta that we want, is 45 degrees. Okay? So, ladies and gentlemen, what that is going to tell us is that we want to find what N value would give us a critical angle response if our theta is going to be, or theta 1 is 45 degrees. Now, ladies and gentlemen, remember that we have to be going from a high N value to a low N value in order to get a critical angle scenario. That is critical so that you remember that. So this is the surface between that prism and the air. Well, we know that the N value of air, ladies and gentlemen, so our N2 is going to be 1. And remember that we are looking at a critical angle scenario here. So in critical angles, our theta has to be 90. There we go. Okay. So, ladies and gentlemen, let's go and set up what we have with our calculation here. So we have our theta 2 is 90 degrees. And then we know our N1, N2 value of air is our 1.00. No units, it's a unitless value. And we need to calculate our N1. So what would N1 be if this was our critical angle scenario? Okay, well, you're going to go back to your beautiful data sheet, and we know that sine theta 1 divided by sine theta 2 is equal to N2 divided by N1. And we now need to find our value for N1. So you got a couple ways you can do this. You can rearrange, or you are welcome to go cross multiplying and dividing. Whatever you want to do, show your work. Okay, so I know what it is you're doing. And so we're going to rearrange this, ladies and gentlemen. I'm going to multiply by N1 in order to make this linear. So my N1 sine theta divided by theta 1, divided by sine theta 2. And then I'm going to multiply by sine 2 divided by sine of theta 2 divided by sine of theta 1. And that is then going to give me my lovely rearranged equation. It's going to scroll down so I've got space. Okay, so my value of N1, ladies and gentlemen, is going to be N2 times sine of theta 2 divided by sine of theta number. Let's actually write numbers in the right spot here. Let's get rid of that. There we go. It's Monday, and it actually is Monday for once. Okay, so ladies and gentlemen, theta 2 divided by theta 1. All right. So, ladies and gentlemen, you're going to put your lovely numbers into your equation. And N2 is 1. And we're going to multiply that by our sine, and theta 2 is 90 degrees. And then we're going to divide that by our sine of theta number 1, which is 45 degrees. And when you get your final answer, ladies and gentlemen, we have our 1.414 ... remembering that n is a unitless number. And with sig digs, okay, we get our n is 1.41. Now, once again, remember, this is the minimum value for n. So, because in order to get total internal reflection, the n value has to be higher than that of the critical angle scenario. Okay, so ladies and gentlemen, I hope you guys enjoyed that. I did post on Google Classroom a fun video about the use of refraction in creating of super cool lasers. Other cool uses of understanding how light behaves in refraction is actually what makes gemstones shiny. So when you look at a ring that has a gemstone in it, so my engagement ring, for example, a couple small diamonds in there. So what makes diamonds sparkly is the fact they've been cut at certain angles, so that way the light is going to refract in certain manners. So that is another application of why this is important, as well as getting a fiber optic cable to deliver your wonderful telecommunications right to your house. All right, so I hope you have a good day, ladies and gentlemen, and we will see you all tomorrow. No fires, injuries, or explosions.